Good morning, everyone. My name is Karol Dziki, and I am a PhD student of the Faculty of Mechanical Engineering of Silesia University of Technology. I want to briefly present to you a paper that describes a method of solving mixed model assembly line sequencing problem, which was developed together with Professor Timon Krenchik. Modern production systems are defined by customers' requirements. Customers expect that product will meet their specific needs, and they are more willingly to choose those products that are customized for them. This is a reason why mass customization is now the most popular approach in mass production systems. Thus, high versatility approach is related with higher production costs and more complicated production lines and processes. Solution for those problems is usage of mixed model assembly line that combines lower cost of mass production with high versatility of customer approach. When designing mixed model assembly line, the three basic problems need to be solved: balancing of assembly line, sequencing of production orders, and part filling problem for efficient supplying assembly line. In this case, we assume that assembly line that need to be solved is already balanced. Demand for each version is determined, and processing times are known. Transportation to patients are ignored as inessential with daily processing times. As a result of solving mechanism, a near-optimal sequence of production orders will be defined. For finding final solution, a simulated annealing algorithm was chosen as suitable for this NP-hard problem. Simulated annealing is based on metallurgical phenomena. Algorithm is searching for a solution in a range that is defined by a factor that is called temperature. It represents the possibility of choosing a possible solution given the scope of potential solutions. For each chosen solution, objective function value is calculated, and the best score solution becomes the center of new searching scope. The scope is narrowing every time new best solution is chosen as the center point. Simulated annealing algorithms have mechanisms to avoid local optima. First one is that any chosen possible solution have given probability, depend on the temperature value, to become a new center of searching scope. Another one is so-called reheating. It's the setting of temperature value in center of searching scope for increasing searching rate. Proposed modification of SA method define possible solutions as randomly generated sequence. Its sequence have form of matrix of binary values, where rows represents production versions and columns are the next positions in sequence. A randomly generated sequence must meet additional requirements. A sum of each row must be equal to the version demand, and only one object can be assigned to one position, so the sum of values in each column must be equal exactly 1. Generating next candidate for solution is carried out by repeatedly sweeping two randomly selected columns, and this operation is correlated with current value of temperature. In production schedule of assembly line, we define sequence of production orders, gaps between operation blocks can be noticed. In case described here, the gaps can appear for two reasons. Workstation is waiting for part from previous operation. Our next operation is blocking station to hand over finished CAD product. Shown formula was defined as objective function for a modified SA algorithm. The goal is to define sequence that maximize the line efficiency. Algorithm objective is to find minimal value of sum of all idle times occurred in production plan and divided by average assembly time for normalization of results. When previous workstation is processing time is Austin current workstation, fee value is calculated, and when the next workstation is waiting for the element, omega value is calculated, and then sum for respectively for each positioning sequence. As an illustrative example, production of 4 versions of product was chosen. Demand for each version is respectively 4, 6, 4, and 3 and 2 pieces. Every workstation performs some operations on each version. It is shown in the processing times are shown in the table, and additional assumptions are defined. Transportation times are small enough to be irrelevant, and it can be ignored. Every workstation is supplied for parts on time, and there are no idle times created by supplying intra-logistics operations. And product can leave the workstation only when the next workstation is complete assembly operations. That means that we don't have a possibility to pass over finished product if the extension is still operating. Simulation was performed in MATLAB environment with modified built-in SI module. Simulation was performed on 500 iterations with temperature decrease factor 0.95 and starting temperature from 100. In the early stage of searching, it can be noticed that the mechanism of choosing not the best solution is working quite well, and it's trying to find another places for best solution. And the best solution, near optimal solution, was found quite quickly, based on that the dataset is not complicated, and this example is quite simple. There was performed another. In order to check whether the found solution is not the local optima, another solution was carried out with a greater number of iterations and with the reheating mechanism activated. Simulation parameters are as shown. Starting temperature value is 100, number of iterations is 900, cooling rate is 0.95, and the I value is equal 70. It's a value of parameter that defines when reheating is occurring. If 70 times in a row same value will be objective function result, then temperature is resetted to 100. In the early stage of search, you can notice again these not best points that are chosen as a solution. After first temperature reset, you can notice that algorithm stack on the local optima solution, but in the next reset it will find early best value, and this best value equal 20.97 was carried derived by the sequence shown here. If anyone have some questions about this paper, feel free to contact us, and thank you for your attention.